Okay, so this is the presentation. So I'm going to start from the beginning. Demonstration of a distributed computing network with a hybrid client-server network by Josh Johnson. The graph shown here is the motivation for this work. When the first computers were introduced in microprocessor form or even discrete form before that, they had a clock frequency in the kilohertz range. The clock frequency is the rate at which the processor can compute the information. The graph before you shown here shows the trend in what's called frequency scaling, or the clock frequency of various computer processors over time. So it reached the double-digit megahertz in the early 80s, and it continued up as shown until about the year 2004 or 5. As seen towards the recent parts of this graph, it has not increased since that time. In fact, as the graph shows on the scatter plot on this slide, it's actually stagnated, in some cases has been reduced for processors that are meant to use less energy, but it has not increased to 10 gigahertz as Intel engineers wanted to allow in the early 2000s. This is a limitation in how fast computations can be done, because an addition on a microprocessor requires at least one clock cycle, and since they're not increasing anymore due to physical concerns such as overheating and the nature of high frequency electronics, it's led to a concern in the future trajectory of computing. So one solution to limitations in what can be done with integrated circuits is distributed computing, which is demonstrated in this module. This methodology allows multiple hosts to work on a problem in tandem. Basically, it applies division of labor to mathematics. So although we might not be able to have a 10 gigahertz processor anytime soon, you can always add more hosts to a network and distribute the work among them. Now, one might wonder if there's any limitations, and the answer is yes. Something called Amdahl's law, or Amdahl's argument, enumerates this. So for example, you can only use distributed computing, or equivalently parallel computing, if the steps can be split in the mathematical labor, if you will, executed by multiple computers. If you have a process by its very nature that requires an answer from a first step to obtain an answer from a second step, the method here is not applicable. And a man named Amdahl, who worked at IBM for many years, quantified this in the late 60s in Amdahl's law, which basically states the fact that you can only speed up the parts of a parallel calculation, which can be divided among several computers. If it has to be done in sequence, the parallel trick here does not work, and so there's an upper limit on how fast you can speed up a process. Okay, so basically I implemented a client-server architecture that demonstrated distributed computing. The calculation utilized were numerical integrals, which can be split into several partitions integrated by each separate client, or client server technically, and then put back together. So basically the server worked as follows. The program began, the server's constant IP address was set, the socket object was set, and then it bound and listened to that socket. The server would then wait until at least two clients joined, as shown in this loop here, and it would add them and set up their sockets using the .accept method. And from there, a problem would be entered using the easy GUI, the easy GUI interface. The integral parameters were entered at the server side, and in theory it could be done from the client side, although the client compilers did not have easy GUI installed, so I didn't pursue this. The integral was then divided into partitions, as mentioned, and each partition was sent using the .send method to the remote clients. From there, the server would wait for a response using the .receive method, And from that point, the subsequent integral partial answers were sent back from the clients. They were added together as shown by this loop here, right here, and the final answer was then obtained as a sum. The blue line shows how another problem could be entered, or if the server user so desired, the program would end. The client was relatively simple compared to the server. The program began, the client would connect to the constant IP address of the server. Threading began. Now, these flowcharts are approximate because threading greatly conflates the difficulty in drawing a flowchart because it involves several processes happening in parallel. But essentially, the flowchart here shows the effective order of the operations. So then, the name of the server was entered, converted into ASCII, and sent to the server, shown by this arrow here. The server would then send the partition, which was then converted back, the partition sent here. It was then converted back to the mathematical figures. The partition sent to each of the clients was an actual string, which had to be converted back to the original numbers because you can only send strings easily. From there, the client would work the partition as a Riemann sum, as shown in this box here. I'll explain that momentarily. Once it had done its end of the computation, it would send the one thing back to the server. Now, in a strict client-server architecture, the server does the work and sends it back to the client. The client only sends requests to the server. In this case, I made an exception, allowing the client to send back one thing it's computed to the server, the partial answer for that partition, which is sent back, and that links to the other flowchart I just showed. The client then waits for the server's reply, which would be the answer to the integration problem, and then displays the results when received. From there, it loops back infinitely, so other problems could be distributed. Now, the take Riemann sum box in the bottom left there actually runs the summation shown right here, essentially performing rectangular integration. In this case, I use the function of the form of a polynomial, ax cubed plus bx squared plus cx plus d. This was done simply because polynomials are well understood, and of course any function could be used, and you could use a separate library to convert the partition string, which is sent from here, into the right form. And as mentioned, these parameters are sent to each. So basically, it's a simple demonstration of distributed computing using a type of problem that can be distributed. Now, the results, which of course were shown on video, are pretty interesting. So basically, the top blue lettering in the top left of the slide is the server, and the two windows shown in the bottom are the clients. So first, the two clients have to connect to the server. First one on this line, Alice joins. I named it that. The second one is Bob, and it joins. And this is Alice's IP address and port here. This is Bob's IP address and port here. Then the problem is entered. After this point here, easy GUI inner box allowed entry of the problem. It's not shown here. Then the problem was partitioned as shown in these lines and distributed. Each of the clients did its part and sent the result back, and as a result the final integral was found. So the integral of 4x cubed plus 3x squared plus 2x plus 1 from 0 to 20 is approximately 168,422, and I ran this on my TI calculator, and it has 5 digits accurate. And as you can see how this works for this problem using the fundamental laws of integration. So the integral of a function from 0 to 20 is the same as the integral of the function from 0 to 10 plus the integral from 10 to 20. So integration has a form which can be divided and conquered like this. Now, as I've mentioned, this only works for certain types of mathematical problems. In other problems, you have to have all the sequential steps executed in order. In other words, you have to have the answer of a first step to begin a second step. In such an instance, as aforementioned, it is impossible to use this trick, but it works for many problems. So, as seen in this command prompt, Alice receives a string. Again, these are the coefficients: 4x cubed, 3x squared, plus 2x plus 1. On the string is where my pointer is. That's what those signify. You might wonder what the rightmost 3 digits represent. The 10 is the range of over how long you're going to integrate. The small number, 0.0001, is the numerical differential, which can be altered at the problem entry phase. And the last digit is where you begin the integration. In other words, I'm sorry, my pointer keeps disappearing. This one runs from 0 to 10, and this one starts at 10 and runs for 10 or 20. The differential is the same. So as you can see on the slide, the blue integral is done by Alice, the red integral is done by Bob. They're added together at the server to get the black integral, which is the number it's pointing to here. This worked in practice, and the video demonstrates this. And this is the link to the video. I'm not going to pull it up, but it shows exactly what I just mentioned. This is what I was mentioning earlier, the Amdahl parallel computing law. So basically, it's an upper limit as to how you can divide and conquer. In short, it works like this. If you have a problem which can be divided into a parallel portion for half of its work, then you can only speed it up by a factor of 2, because in the ideal case you have an infinite number of computers working on it, and the half that's parallel, the delay goes to 0, but the other half cannot be inherently divided into parallel threads. Accordingly, it can't be sped up. But the greater the parallelism of the process you're doing, the higher the potential speed up. So for example, in the extreme instance, if 95% of a problem can be divided into parallel sections, then the greatest speed up you can achieve is 20 times, or 0.05 times the initial delay. So yes, there is a limit with distribution of computing, but as clock frequencies and the number of transistors you can add to an IC seems to have been gradually declining in its growth, this method has been investigated as a clever trick to continue performance enhancements despite these obstacles. Uses of distributed computing, the most famous one is the search for extraterrestrial intelligence, or SETI, and they, since the 1990s, have used this methodology to allow radio telescope data to be filtered and analyzed by a large number of people's personal computers over the internet. Although SETI has not found conclusive evidence, or really much evidence, for extraterrestrial intelligence, they've proven a good terrestrial point, a solid point, that you can use distributed computing for research in a way that is effective. Since that time, many individuals in other universities have employed this concept. So the work herein leads to a list of conclusions. Yes, socket programming can implement client-server applications in Python. The client-server paradigm can be modified in a form that allows distributed computing. The modification, the biggest one, is that the client sends back information to the server. This only happens once, and the only information it sends besides the request is the partial answers, because it's inherently difficult to scale a central server, as mentioned in lecture. Distribution of computation can have benefits, this was mentioned, but it has limits, namely the effect of Amdahl's law, which I mentioned before, and that puts an upper limit on how you can divide and conquer. And as a result, this project was successful in investigating a simple example of distributed computing. If I were to work on this further, I would have taken rates of computation in statistics and have analyzed this further, but I can say, based on observing the system at work, that dividing the integral into 2 partitions roughly doubles the speed at which you can do it, because only a single addition is required to combine the 2 partial answers into the integral, and a majority of the time is lost summing up a bunch of terms. This essentially concludes this project and this presentation thereof. Here are the references. The first one is statistics on processing power. The second one is a manual for Python, and the third one is SETI's website. Thank you for your time, and this concludes my presentation.